my friends, and welcome to another Science video. In this one we're going to be looking at covalent bonding, covering what the bonds are, how to draw them, and what small and large covalent structures we can find and what properties they have. Let's get to it. If you've seen my other video on ionic bonding, you know that bonds are things that cause ions or atoms to stick together. In this video we're focusing on covalent bonding, and in covalent bonding it is the sharing of electrons. These are sharing of electrons between atoms. These are not charged atoms or ions, they are just atoms, and they are sharing electrons in their outer shell. That sharing of electrons is leading to them having electrostatic forces holding them together. And this again is still trying to make sure that they get a full outer shell of electrons. So the chlorine here is sharing its electrons with the partnering chlorine, and they both end up having 8 electrons each in their outer shell. So chlorine here has 1, 2, 3, 4, 5, 6, 7, 8, and its partner chlorine has 1, 2, 3, 4, 5, 6, 7 originally, with now an extra 1. So let's look at how this works in a bit more detail. So we've already established that covalent bonds are where electrons are being shared. They're not being given from one atom to another to make ions, like in ionic bonding. It is the sharing of electrons between 2 or more atoms. And this is only going to happen between 2 non-metals. So it's the metals from the groups 5, 6 or 7 typically, sometimes group 4 as well, that will do that. And that's because they all need to gain more electrons. They all need to gain more electrons. And so what they will do is they will share some of their outer shell of electrons to enable them all to have a full outer shell. So in the example here of ammonia, we have nitrogen, which is found in group 5, so therefore it has 5 electrons in its outer shell, and it needs to therefore have 3 more electrons from another source. So what it does is it shares 3 electrons from 3 different hydrogen atoms. So we've got 1 hydrogen here, 1 here, and 1 here. And these hydrogen atoms all are in group 1. The hydrogen needs to gain 1 more electron too, so it also shares an electron from nitrogen. So here we can see a nitrogen electron in each of these hydrogens, and we've got also a hydrogen electron being shared. So this hydrogen now has 2 electrons, which is its first shell being full. This one has 2 electrons, its first shell is full, and this one also. And the nitrogen had 5 electrons originally, 1, 2, 3, 4, 5, and it's gained another 3 through the sharing of electrons from the hydrogens. So every atom here now has a complete outer shell of electrons, and they are all stable, which is fantastic. But what we need to note here is this is what we call a dot-cross diagram. We use dots and crosses in the ionic bonding too to represent the electrons that have come from different types of atoms, but here we're using dots and crosses to show the overlap regions of where electrons are shared, and using dots for one atom and crosses for another means that they are easy to distinguish between different atom types. We can see where they're being shared from, but we can also draw these types of bonding in a different way. So in this first example we've drawn rings to represent the atoms. That's how we're going to draw them. That's the typical way that we will do it. You also might see these kind of drawings where the rings are not drawn. So you imagine the ring here of nitrogen and the hydrogen and the hydrogen. They're not drawn there at all. We've just got the pairs of electrons being shown. So I've got a dot and a cross, dot and a cross, dot and a cross. Those are the sharing electron pairs, and then this one is just what was left over in the nitrogen. We've also got different type of bonding structure here, which is shown. The electrons aren't drawn, but the bonds are represented with sticks, and that's one way of representing the structure. And you'll see that a little bit later, how I draw water is drawn that way. The sticks here are bonds, and we can represent ionic bonding in the same way. And then there's also a ball and stick diagram, which shows the 3D structure a bit more, and it also represents the size of the atoms. But all of these are models of these atoms. None of them show how the actual atoms will behave when they're with each other. So it doesn't show how they exist in a 3-dimensional shape necessarily. The ball and stick comes pretty close, but it also doesn't show how they're actually moving all the time. These have kinetic energy because remember they have energy because they're not at absolute 0 temperature. So they have energy and they are moving around, and no picture is going to be able to show that. But these atoms, they are sharing electrons, and therefore they do not become ions. In ionic bonding, they're giving away and gaining electrons, so the atoms are actually gaining or losing electrons, and therefore they're becoming charged. In this case, they aren't. They're just merely being held together very closely, and that very particular way of being held together is what we call a covalent bond, and it is a very strong type of bond. We're going to look here at how we can draw covalent bonds, because this is a skill that we need to be able to have. We need to draw them for some fairly simple molecules, and we'll try some examples of these in a bit as well. But we need to be able to draw them from simple diatomic atoms like fluorine bonding with another fluorine, or oxygen with another oxygen, or nitrogen with another nitrogen. But we can also look at pairings or trios, or even sets of 4 or 5 atoms, or even more than that, where they're bonded in large molecules of covalent bonds. So hydrogen and oxygen there, for example, will bond together to make water. So we're going to work through the steps that we can follow to try and do that, and the first two are very similar to that for ionic bonding. So first up, it's important to establish how many electrons they need to gain through sharing rings of electrons. So it's worth and it's good practice whilst you're learning how to do covalent bonds to do these first two stages. So first we draw the electron configuration of the atom. So that's nice and important. We use dots to represent the electrons on one and crosses on the other. So for fluorine here, we know that fluorine is in group 7, so it's going to have 7 electrons in the outer shell. So we can draw those first. 1, 2, 3, 4, 5, 6, 7. And because it has that outer shell, we also know that it's got 9 electrons in total. It must have 2 on its inner shell, which is of course complete because we fill up the inner shells first. For the other fluorine, it's exactly the same. We'll do dots for this one though. 1, 2, 3, 4, 5, 6, 7, 8, 9 in total. So then the next part, that's that bit done. The next part, how many electrons does each atom need to gain? Well, the fluorine here has 7 in its outer shell. It's a structure of 2, then 7. So it needs to gain 1 more in this shell for it to have a full outer shell. And this one's exactly the same. It needs to gain 1 more to have a full outer shell. And so what we can do here is think, well, how could they share their electrons to give each other what they need? Well, if we draw here now in stage 3, we've got the outer shells are overlapping. And so in this diagram, we can see that there is an overlapping region, this bit here. And here is where we're going to draw the electrons that are being shared. We need to think how we can overlap the outer shell of these fluorine atoms to give them a full outer shell each. So the way that we will do this is because they each need to gain 1 more electron, they can each share 1 whole electron. So we've got one of the dots and one of the crosses from each of these atoms. We've got 1 electron being shared in this overlapping region. If we draw then the rest of the electrons onto the shell, for the left-hand fluorine, it had 7 electrons in its first shell. We've got 1 drawn, so we'll draw the other 6. 1, 2, 3, 4, 5, 6. And for the dotted fluorine, we've got 1 already, 2, 3, 4, 5, 6, 7 in total. That's how many it had in its outer shell. But now, because of this overlapping region, each of them has gained 1 whole electron. So this left fluorine has got 1, 2, 3, 4, 5, 6, 7, 8. And the right-hand fluorine, 1, 2, 3, 4, 5, 6, 7, 8. So they both now have a full outer shell. And that's how we draw our covalent bonds. Just a note here that you can do this in a slightly different way. You can draw them in this region in the middle. You can, where I have drawn them here, I quite like to do it because it's quite nice and clear then, but you can also draw them on their electron shells still where they would originally be, as the diagram above, and it shows that they're then being overlapped. And you can also do them, as you saw in the diagram a little bit earlier, at the actual crossing point of the electron shells too. But sometimes you might have more than 2 electrons in this space, so it gets a bit difficult to do that when we've got some more. Okay, I'm going to throw it over to you. There's going to be some examples that you can try and do. So the 3 examples here that we're going to do. The first one, oxygen, is nice and similar to fluorine. Just double check that it's in group 6. So being in group 6, it needs to gain 2 more electrons. That's a clue for the first one. For hydrogen chloride, hydrogen is in group 1. It's got 1 electron only. So we're thinking in terms of shells, it needs to make up from 1 electron to fill its shell. It needs just 1 more because the first shell only has 2 electrons in it. And chlorine is in group 7. I'll let you work that one out. For water, it's a little bit more complicated because now we have 3 atoms. Oxygen is in group 6, it needs to gain 2 electrons, so it's bonded to a hydrogen on each side. And I've drawn it there in the way that it's going to be represented. That's the ball and stick kind of version of what water will look like. And you need to think about how the overlap's going to work there. Give it a try, and I'll talk you through it in a moment, and then you can come back and try again if you're still stuck. So if you've tried these, we're just drawing the outer shell here. I'm not doing stages 1 and 2, I'm just doing the overlapping parts. So for oxygen, they're in group 6, so they have 6 electrons in the outer shell, so it needs to gain 2 more in each of these atoms. So they each need to share 2 electrons. So 2 dots and 2 crosses. For the left-hand side, if we make the left one a crossed atom, it's used up 2 electrons there already, so it's going to have a further 4 in its outer shell. So it now has 1, 2, 3, 4, 5, 6, 7, 8, a full outer shell. Fantastic. The one on the right will make it the dotted one. It's used up 2 of its electrons already in the shared region. It now has 4 left. 1, 2, 3, 4. Fantastic. In total, let's double check. 1, 2, 3, 4, 5, 6, 7, 8. Excellent. For hydrogen chloride, hydrogen has 1 electron, so it needs to gain 1 more. Chlorine is in group 7, so it also needs to gain 1 more. So each of these atoms can share 1 electron in this shared overlapping region. Hydrogen has 1 electron, and that 1 electron that it has is in that overlap region, so there's no more that we need to draw for hydrogen. For the chlorine though, the chlorine has 7 in its outer shell. We've got 1 in the overlap region, so we need to draw the other 6 in the rest of its outer shell. I'll do dots here just to mix it up. 1, 2, 3, 4, 5, 6. And in total, hydrogen has 1, 2. Fantastic. It's just that first shell that it's trying to fill up, so 2 electrons is perfect. For chlorine, 1, 2, 3, 4, 5, 6, 7, 8. And for water, hydrogen again only needs to gain 1 more electron, so we just know straight away it's going to get that from this overlapping region. And the same on this one. And oxygen is in group 6, so it needs to gain 2 more electrons. Well, we've already included those by having them shared by the hydrogens, and we've got to draw the remaining electrons on the oxygen outer shell. So it's in group 6, it's got to have 2 electrons being shared, so that leaves it with 4 left that we can draw on. I'll do crosses in this case. 1, 2, 3, 4. And again, if we just check for our mistakes here, we check it's got the right number. 1, 2, 3, 4, 5, 6, 7, 8. It's got a full outer shell, and each hydrogen has the 2 that it needs for its outer shell. Fantastic job. So now you've mastered how to draw these substances, these covalent bonds. Let's talk about what properties covalent substances have and how they compare to ionic and metallic structures. So firstly, we need to know that the covalent bonds themselves are very strong, but these only stick the atoms together in a molecule. So they are these bonds sticking the hydrogens to the carbon in a methane, or the oxygens to the carbon in carbon dioxide, or the hydrogens to the oxygen in water. The thing that makes something a liquid or a solid or a gas is the intermolecular forces between molecules. So it would be the forces holding carbon dioxide together. But for these molecules, for small covalent substances like these I've drawn for methane, water, oxygen, fluorine, chlorine, carbon dioxide, the intermolecular forces are very weak. So as a result, they have very low melting points and low boiling points, and this means that we don't need to put in much energy to separate them. So again, the bonds in between the atoms in the molecule are very strong, but the forces between more than one molecule, so this here is a molecule, this is a different molecule, the forces between them are very weak. So to turn carbon dioxide from a solid to a liquid doesn't need much energy, hence why it's a very low melting point. And to turn it from a liquid into a gas, again, we just need to give enough energy to separate these bonds, and we don't need to give much at all, so the boiling point is very low. And also, in comparison to ionic structures, these don't conduct electricity ever. They're not ionic, they're not charged, they're not ions, and electricity is the flow of charge. If these aren't charged, they can't conduct electricity. But you will see that there are a couple of examples in a moment that can. Now, what is extra to note here, that they do have low melting and boiling points, but as the molecules get larger, the forces between them get larger. And that's because the force of attraction is between the electrons and the nucleus, the protons, of the neighbouring molecules or atoms. And so the more electrons and protons there are in the bigger atoms and the bigger molecules, the more force of attraction there is. So in the very large, let's say group 7 elements, like chlorine, is much larger than fluorine, and so it has much greater forces of attraction between the electrons and the protons of different atoms, and so the intermolecular forces are much greater. We also have some large covalent structures. Large covalent structures have lots of covalent bonds in a very large mesh, and this large mesh leads to formation of what we call giant covalent structures. And if you imagine a solid, these are solids typically that have covalent bonds between every single molecule or atom. And so these end up being very large, very strongly held together. So as a result, they have a really high melting point and also a really high boiling point. So it's really difficult to break the bonds. This isn't just intermolecular forces that's holding them together anymore, it's covalent bonds. So we have to put in lots and lots and lots of energy to try and break them apart. Now, silicon dioxide is an example of this, which is here on the right. It's just a really quick example. But that is one that ends up being a very large structure. It's silicon dioxide, SiO2, and it's found in glass and sand and that sort of thing. And that is a prime example. And the other examples are carbon and forms of carbon like diamond and graphite, which we're going to look at more in a second. So there are three main categories of what we call allotropes of carbon. And allotropes just means different structures of carbon and how carbon can be found. But this is carbon as we know it in the periodic table. The first one that you're probably most commonly aware of is diamond. And in diamond, every carbon is bonded to 4 other carbons. Now that's important because in comparison, graphite is only, the carbon is bonded to only other 3 carbons. So that's a critical bit of information that you first need to make note of. Now, diamond, as you know, is very strong. And it's very strong because of each carbon being bonded to 4 others by covalent bonds. So every single one of these bonds here is a covalent bond. So it's super, super strong, super high boiling point. And you end up getting this really large structure where every single one is bonded to 4 others, which is bonded to 4 others, and so on and so on and so forth. So it's a very, very strong structure, super strong. Now it can't conduct electricity, but the other molecule we've already mentioned here is graphite. And graphite can conduct electricity because every carbon is bonded to 3 other carbons rather than 4. Now carbon is in group 4, which means it needs to find 4 electrons to make a full outer shell. Now it can do that in diamond very easily because every single carbon it bonds to shares 1 electron, and therefore it gets 4 electrons shared with it, and so it gets a full outer shell. But for graphite it doesn't, because every carbon is only sharing from 3 other carbons. So what it does, and what these structures are found to have, is a hexagonal structure, a hexagonal shape. And that hexagonal shape means that there is an area in the middle of this hexagon where we find delocalized electrons. And that's a really important key word. Delocalized, if you think of local being in the local area, in the near area, these electrons are delocalized. So they're no longer found in the electron shells in 1 carbon. They're located instead in this common area, a shared space of electrons, if you like. So it's not just one overlapping between one atom and another atom, it's an overlap between all 6 of these carbon atoms. And so all of these electrons are shared in that space, and the electrons in there can actually flow freely. So if they can flow freely, they can conduct electricity, which is really, really interesting. So this is a covalent structure that can conduct electricity. And graphene is simply just one layer of graphite. Now graphite is made up of lots of these layers of graphene, which are basically these hexagonal structures all linked together. But they exist as layers. So this is graphite, but graphene is one individual layer. And there are weak forces holding these together. They're not bonds, they're just weak forces. But that means that these layers can slide past each other. This one can slide that way, this one can slide that way. And that's what makes graphite really useful in pencils, because graphite, when you write on pages, the graphite will rub off onto the paper because of this layer-like structure. And graphene is one of these individual layers. And graphene on its own is very, very, very strong. It's super strong. It's going to be used in all sorts of future technologies once we've figured out a way of producing it on a mass scale. And it also can conduct electricity. So it's very thin, very strong, and can conduct electricity. So it's really going to be very useful. The final group of allotropes, which are these alternative structures of carbon, are what we call fullerenes. And fullerenes tend to have a similar kind of shape as graphite, and they can fall into different categories. So there's some called the Buckminster fullerenes, which are more kind of spherical shapes, and they can be used as a lubricant because they're spherical, but they're strong. They hold their shape very well, but they're very small spheres, and the spheres can lie in between structures and therefore act as a lubricant because they can roll. We also can make nanotubes, very, very tiny tubes of cylindrical, if you like, hexagons, and these end up having a very high length to diameter ratio. So compared to their width, they have a really high length, and they can do, and they end up being very strong too. So when we look at nanotechnology, if you do chemistry rather than combined science, it's something that can be really useful in electronics and making strong materials. If you've got any questions or queries or any challenges you want to set, feel free to add them in the comments. Give me a like, give us a subscribe as well, and check out the other videos we have on chemistry and bonding.